Yeah, so last video we started discussing embedded methods for feature selection, and as an example we saw L1 regularized logistic regression. So with embedded methods we mean methods where the feature selection is part of the model that we are training. And today we will see another example of embedded methods, namely decision trees, and how decision trees again select their features at each node, and then also how it relates to random forest feature importance, where random forest feature importance is probably something you have already seen or heard about, and today we will see how that actually works. And like a small announcement to make, so my iPad pencil or pen doesn't really work anymore, so I switched to a pen tablet, and I heard it's quite a learning curve, and I'm noticing now it's actually trickier to use than I thought. So it will maybe take me a few videos to get really comfortable with it and used to it. And I'm also trying out new software here for the screen annotation. So please be patient with the annotation. I hope it becomes smoother in the upcoming videos. So just as a small side note here. So the broad category of feature selection, just once more, we have the filter methods, the wrapper methods, and today the focus is on the embedded methods. Last week, the lasso or L1 regularized regression, and now the decision trees and random forests. And once we have these parts here done, once we check those off, we will move on to these wrapper methods, where we will talk about methods where we use explicitly an algorithm to do the feature selection. And again here, the feature selection is part of the algorithm. So let's start by talking about decision trees. And in particular, we will take a look at an example data set first, and then we will just briefly see again how a decision tree would split this data set. So this is an example I took from the previous decision tree lecture. So you may recall this figure I'm showing you. It's quite a few weeks old, but maybe you recall we had two features here, x1 and x2. And there are two classes. There is the square class and this triangle class here. So that's class table 1, and the square is class table 0. And the goal here is to classify the data points like in a regular classification example. So decision boundary, if I delete this, a decision boundary might look like this, for example. So you can see that all the class 1 examples are on one side, and all the class 0 examples are on the other side. So that would be one possibility for a decision boundary. Another decision boundary, if you look at this closely, could be like this, where we partition off this space here, or these as one class. So everything basically here inside would be one class, and everything outside would be the other class. So let's zoom into that and actually see a concrete example of how scikit-learn would do that. So here I have a decision tree that I actually fit in scikit-learn to classify this data set. And if you don't believe me that this is an actual decision tree, you are welcome to go back to the decision tree lecture where we had this as a code example. I should probably also put the links again under the video so you can then double check and run the code yourself. So what's going on here is that we have a decision tree that does two splits. So the first split is this one here. That's split number 2. And the second split is this one here, where it's splitting on another feature. So here, this is the bare bones scikit-learn representation of a decision tree. So you can see here first, it uses x1 to make a split. And in particular, it says 5.5 is the cutoff here. So we have here 5.5 as x1, the cutoff. This is our first split here. And then we have the second split here, this one, and if we look at this, we have x2 smaller or equal to 10.5. So where might that be? 10.5, that's here. So here's actually our second split going on. Okay, so we have two splits here, and we can see based on these splits, the classifier classifies this data set perfectly. Now, a little bit more information here. So we start out with an entropy of 0.985, which is relatively high. So the highest entropy for a binary classification problem, if you recall, is actually 1 if we have two classes. And it would be 1 if the classes are perfectly matched, perfectly mixed. So here we have 4 and 3. So an entropy that is almost maximal. Maximum entropy would actually be if we had, let's say, 4 and 4 or 3 and 3, if we had an equal class distribution. Because entropy is a measure of, let's say, how organized something is, or how pure something is in terms of mixing. And we have a highest or perfect mix if we have equal proportion. So a high entropy means a high mix of something. And here, when we split, we reduce the entropy to 0 and here to 0.811. So there's a reduction in entropy here happening from 0.9 to 0.8 and also equally to 0.0 if we use that feature. Then we still have entropy of 0.8 here, and we want to get down to ideally 0, because if we have an entropy of 0, that's the ideal case where there is no mixing. That means we have class labels all of one kind here. And if we then split on feature 2, we can see we achieve this very low entropy of 0 here. So that would be the ideal case. I'm just emphasizing the entropy here because we will be reusing that when we talk about random forest feature importance. But one thing you can already recognize here, if I delete the annotation for a second, so one thing you can already recognize here is that decision trees have to decide which features to use. So there is a feature selection going on here implicitly. So in logistic regression, all the features are used all the time. It's a weighted sum, except of course when we use the L1 penalty, where some features get zeroed out, right? Here, we only use one feature at a time. There is no weighted sum. First, it decides to use feature x1, and then it decides to use feature x2. And how is that decided? It's essentially looking at what is the feature that minimizes or decreases, decreases the entropy the most. So decrease entropy the most. And instead of entropy, we also learned this could be, for example, the Gini impurity, or in general, it could be any impurity measure that we have. There's also a flavor of that we talked about in the decision tree lecture. That's maximizing information gain. Maximizing information gain. And if you don't recall how that worked, so we can also then, I can link the lecture, the decision tree lecture, where we had discussed information gain in detail. But for simplicity, you can also think about it as minimizing the entropy, or trying to get the biggest change from entropy here, like minimizing the entropy as much as possible as one criterion for selecting which feature goes here and which threshold goes here. Moving on, another example here. So here this would be a different way to split the tree. So first, the decision tree uses feature x2. So here splitting first on x2 smaller or equal 10, and then again splitting on x2 again at 7.5. And if you split the decision tree like that, then you can also reach 0 entropy here, which is the ideal case. So we also have a pretty steep decline in entropy. And in effect, that's the same as before. So both are possible ways to build a decision tree that has exactly the same performance. So I think it's pretty easy to see that decision trees perform feature selection implicitly. So let's go now to a more interesting example and talk about random forests. And for that, we will be looking at a wine dataset that I already introduced in the previous video. So in particular, the wine dataset has 13 different feature labels: the alcohol content, malic acid ash, alkalinity of ash, magnesium, total amount of phenols, flavonoids, and so forth and so forth. So we have many features here. And let's say we are interested in also understanding which are the most important features that are used in a random forest, because knowing about the feature importance can also help us interpret certain features. And we could technically also select features based on the random forest feature importance for other models. So we could technically use random forest feature importance, select the most important features, and give that to a model that is more sensitive to the curse of dimensionality, for example, k-nearest neighbors. So here I have the code example just for loading the wine dataset, and there's nothing special about it. We have already used that code before. And again, I will be also uploading the full code notebook to GitHub and share the link so that you can also toy around with all the code. So here I have just screenshots because it will make it more efficient to discuss, so that I don't have to switch to a Jupyter Notebook during the annotation here. So here I'm showing you a feature importance plot by a random forest. Before maybe going over the code, let me just talk a little bit about this figure, and then I will show you with the code how to create this figure. So these are feature importances computed by the random forest. And one property of that is that they sum up to 1. So if we have, let's say, f as the feature importance, if I take the sum, well, the feature importances, they should sum up to 1. They're basically just normalized that they sum up to 1. And I have each feature here, each of the 13 features in the wine dataset. And also everything is sorted in descending order, so that the highest feature importance is here on the left-hand side and the lowest feature importance here is on the right-hand side. I will show you how we get this plot from scikit-learn, and then in the upcoming slides I will explain you how that's calculated. So here on the left-hand side I have the code. So we are using a random forest classifier, and we're just using 500 estimators. We can also make this larger, 1,000, 10,000, just arbitrary number here. Use a random seed so that we can reproduce the results. And then I'm fitting the random forest on the training data. So I haven't shown you the code for loading the data, the training data, or let's say for splitting the wine data into training and test. But I have the code in the code notebook, and it's exactly the same code that we used also in the last video. So the key point here though is that after fitting, we get these feature importances from the random forest. So we get these importance values. And these are, these values you're seeing here on the right-hand side. So these are the bars, the magnitudes. It's floats, so between 0 and 1, and such that they sum up to 1. And one thing I'm doing here is I'm actually sorting them. So I'm getting arcsort, or I'm using arcsort, which gives me the sorting order. So it gives me the sorting indices. Why do I need them? It's just for sorting and plotting this plot here on the right-hand side. So what I'm doing here is, when I'm plotting this bar plot, is I'm looking at the range of all the features. So that's like a value between 0 and 13. And then I'm getting the importance values. These are the sorted importance values, right? Because I used arcsort. With arcsort, I get the sort order, and then if I do the indices selection here, it will give me the importances in the descending order here. So the descending order comes from this -1 here. Otherwise, I would have ascending order, so that they would be going from smallest to highest, essentially. Okay, so this gives me these bars in the sorted order. Why did I use these indices here and didn't sort directly? That's because I also want the feature labels here in the right order corresponding to these bar plots. So what I'm doing here is I'm getting the feature labels, which are just the columns of my pandas data frame. And then once I have that, I'm using my indices here to get the labels here, right? So, and again, this one is just the x-axis ticks between 0 and 13 again. So it's just 0, 1, 2, 3, up to 12. And here, this is really the part where I get the actual labels here. Okay, and this is it. So here I'm just doing a cutoff so that it looks nicer here. The cut points look nicer, but that's essentially it. And these are the feature importances. And now by just looking at this plot, let me maybe clear the screen here. By looking at this plot here, what we can see is that proline is most important and ash is least important. And I will show you now how this is computed. And then I will also show you, let's say, some caveats when interpreting this. Yeah, and like I said, we will be discussing now how the feature importances are computed. And one thing about random forests that you recall is that they involve multiple decision trees, right? So actually we can access the decision trees after fitting the random forest using this estimators here. And if I have, like in the previous slide, used 500 decision trees or estimators, I should have a list of 500 of them. So I'm not showing all of them because that would be, of course, too big here for the screen, but we would have 500 decision trees in this random forest. Each decision tree is different, right? Because random forests are an ensemble method and we have to have different trees because otherwise, if they would be all the same, there would be no point in making an ensemble. And if you recall from the random forest lecture, a random forest has two random aspects. One is the bootstrap sampling. So each decision tree gets a bootstrap sample. And the second part is, so a bootstrap sample of the training set. And the second part is random feature subsets at each node. So while the random forest gives each decision tree the full feature set, a decision tree itself uses only a random feature set at each node. And the combination of having this bootstrap sample for each tree and the random features at each node will make all these decision trees here that we have different from each other. In addition, you can also see there's a different random state here for each decision tree used. You can see there's this max features auto setting here. So what does that one mean? So the auto setting, when you look in the documentation, means that it uses max features, square root, and features. So if we have m features, at each node of the decision tree, it would only consider square root of m features. So let's say we have the iris data set and we split a decision tree. We have the iris data set with 4 features. Originally, a decision tree would only consider square root of 2 features at each node. So 2 random features at each node. So in that way, each decision tree would be slightly different from each other. But yeah, that's not necessarily the point of the feature importance. So feature importance could also be computed if we wouldn't use these random features. So, and I will show you now exactly then how, or explain to you how the feature importances are derived from these decision trees. Yeah, and there are actually 2 common ways of computing the feature importance in decision trees. So I will call them method A and method B. So first, let's talk about method A, impurity-based feature importance. And this is the one, as far as I know, that is also used in scikit-learn when we compute the feature importances, as I've shown you in the previous slides. And as far as I know, this is also one of the most popular ways of computing the feature importance in random forests, but it may just be because most people actually use scikit-learn. So how does that work? How does the impurity-based feature importance work? So like the name in impurity-based implies, it's based on an impurity measure like Gini or entropy. It doesn't matter which one you use, it works the same way for both. So let's maybe walk through it step by step. So for each given feature, so we are looping over the features, and if we consider the wine data set, we have 13 features there, right? And then what we do is for each tree, so for each tree in the random forest, and if you recall from the previous slide, we had a random forest with 500 decision trees. What we do is we compute the impurity decrease. So this is what I showed you when we talked about the decision trees earlier. So we had a decision tree where we looked at the entropy, could also be the Gini, but let's say we looked at the entropy here. And then for the child nodes, so let's say we, I don't recall the numbers, but we had like something like 0.98 and then say 0.0 and I think 0.81 or something like that. So, and then we would essentially look at this decrease. So we decreased the entropy from 0.98 to 0.81 and 0.0. And we would actually also add a weight. So in terms of the number of examples at that given node. So that gives us an importance. So if we have more examples at this node, so if we have more examples here, that would give us a higher importance for this particular split. And then what we do is we look at this impurity decrease over all the trees. So first of all, for that feature in that tree itself, and that feature, for example, let's say this feature is x1, we might be using, let's say here, another feature, let's say x2, but then, oops, then we might be using again here x1 and so forth. So we would look at the impurity decrease for the whole tree, how often that feature gets used. And we also do that for all the trees. So we essentially look at all the times a feature is used, and essentially also technically the higher up the feature is in the tree, the more important it is because it splits more data points, right? So the higher up, usually the more important the feature, and this is reflected by weighting by the number of examples. So in a nutshell, how this feature importance is computed, it's looking at the impurity decrease over that feature in the tree and then averaging over all the trees. So it's essentially the average impurity decrease that tells us how important the feature is. The more important the feature it is, the more it decreases the impurity, like the entropy, or the Gini, for example. So we get these average impurity decreases for each of the 13 features here. And once we have that, so these could be some numbers, let's say, depends on how you normalize. They could already be between 0 and 1, or they could be just some numbers that you get there. And then they are normalized such that they sum up to 1. And this is essentially the feature importance that you then get in the random forest. So there are also some caveats with this impurity-based feature importance, especially if we have categorical features with lots of unique values. And let's say you have a random forest based on decision trees that use categorical features. This categorical feature, if it has a lot of values, will be used a lot compared to, let's say, other features, just because it has a lot of values and it has a lot of value for splitting. And then sometimes people think it's kind of like inflated. In fact, I mean, this feature is important for splitting, but it kind of, let's say, disproportionately has a high chance of showing up. And vice versa, if you have, let's say, scikit-learn, a random forest, how you deal with categories is that you do a one-hot encoding, right? And so with a one-hot encoding, what you do is you split a category into multiple subcategories. So you're splitting up a feature essentially. And also then essentially all the one-hot encoded features, they kind of may be essentially one feature, you spread them out, and this can also kind of be a little bit misleading because you're not looking at the original feature anymore, you're looking at that slew of new variables that you create. So you have to kind of a little bit careful with interpreting this. I mean, in practice, if you're aware of that, I mean, it's just kind of reflecting how a random forest uses the feature. So the distinction for me personally, I don't see that as problematic if we really think about what impurity-based feature importance means. And that is basically how a random forest, or how decision trees use these features, right? So one thing is also if you have one-hot encoding where you have one variable that you split into multiple sub-variables, remember at that random forest, we always select, let's say by automatic settings, the square root of m features at each node. So if you have a lot of one-hot encoded variables, or you have one variable that becomes a lot of new variables, then there's a high chance that one of these variables is selected at each node. So this kind of categorical variable will kind of be present at each node at some point compared to, let's say, continuous features. So which can also be sometimes a little bit, let's say, inflating the importance of certain features. But again, I think if we think of these feature importance values as values describing how a random forest or decision tree uses the data set, then I think it's still reasonable to look at these feature importance values. Another thing is correlated features, that they share importance, right? So if you have two features that are equally important, there's a, let's say, random chance to pick one feature over the other. So if we have a feature importance plot, and there are two features that are perfectly correlated, let's say this is one feature and we have two perfectly correlated features, they might then end up like this here. So these two are my perfectly correlated features. And they don't look like in this example, I mean, this is just like something I just made up here, but they don't look like they are super important here in this plot compared to this other feature here. However, because they are perfectly correlated, there's a random chance to pick this one or this one for splitting a node. So in this way, they also share the entropy or impurity decrease, right? Because you use either one or the other, but not both at the same time. So in fact, we are underestimating of how important this feature could be. So if we would remove this feature here, the other feature would gain that importance, right? So in that case, actually this feature might be more important than this feature if we consider that this feature was sharing its importance with another feature. Again, if we think about what is the most important feature in the data set, then this sharing of the feature importance could be problematic for the interpretation. But again, if we think about the feature importance of a random forest is how a random forest or decision tree uses different features, then I think this is totally fine. There is no issue with that. We just have to be aware of how a random forest, let's say, behaves and that there are some caveats. So let me now explain method B for computing feature importance using random forests. And for that, we will have to take a brief look at bootstrap sampling again. I have mentioned bootstrap sampling before when we talked about how a random forest works. And we also talked about bootstrap sampling in the context of bagging in the ensemble method section or lecture. And we also talked about it in the context of the 0.632 bootstrap and 0.632 plus bootstrap in the previous lectures and so forth. Here, the focus is more on one thing I wanted to highlight, and that is the out-of-bag sample. So when we consider bootstrap sampling, so we have the original data set and then we have a sampling with replacement, right? We have sampling with replacement, and because of that, we will have some data points in the data set. So if there are, let's say, data point x1 to x10, they will be then duplicated. So for example, here I have, maybe not a great example, here I have x2 and x2 as a duplicated sample, right? Or x8 and x8 and so forth. And if I have these duplicated training examples in my bootstrap sample, as a consequence, there will be some examples that are not used at all in my bootstrap sample. For example, here x3, x7, x10, and here there was some mistake. There should also be some of them. Maybe did a copy-paste error. In this case here, it's 6 and 9, which are not appearing here. And here there also should be some that are not appearing. I think I see at least x3. I think x7, right, and so forth, x8. So there are always some examples that are not present in my Bootstrap sample, and these we call them the out-of-bag samples. And we can consider them as kind of like test sets or validation, or maybe better, evaluation sets. If you think back about how the 0.632 and 0.632 plus Bootstrap works. And we will also use that concept that we have these out-of-bag samples for computing feature importance. Yeah, let's now look at method B here, the permutation importance. And this involves the out-of-bag samples that I showed you on the previous slide. And in fact, first I wanted to explain to you how we can use these out-of-bag samples to compute the model accuracy. And then we will see how we can use that to compute the feature importance via permutation. And I will actually in a later video also talk about a generalized form of permutation importance. But let's do one step at a time. Let's first see how we can use the out-of-bag accuracy using the out-of-bag samples. So what we do is, during training, we can actually assess the predictive performance of the decision trees or of the random forest. Actually, if you recall from the ensemble lectures, we did that with the bagging classifier, and with random forests, it works the same way. So during training, for each tree, we can make predictions for the out-of-bag samples, which are essentially like validation or test data points to the current tree. Let's say for the current tree, I really need more practice with this pen tablet. But for the current tree, we can, let me rewrite this current. We can think of these out-of-bag samples as validation or test data points because the tree doesn't see them, right? They are out of bag. The tree is only seeing the Bootstrap sample, and then we have these held out ones that the tree is not fit on. And we discussed in the Bootstrap lectures that this is approximately 1/3 of the data. So there should be for each tree plenty of test data points if we have a sufficiently large training set. So what we do is, how do we actually use these out-of-bag samples? So what we do is we consider each training example I and look at all the trees that did not use this training example I during model fitting. So if I have a random forest with 500 trees, there might be, let's say, let's say there might be 100 trees that is not, or maybe fewer, could be 50. But let's say there's a number of trees randomly. It's the Bootstrap samples are random, right? So there's a certain number of trees that is not using a certain training example I. And for these, I can then make a prediction on training example I via majority vote. So I can consider, let's say, the 50 trees that don't use example I and do a prediction on example I. So I get, example I. So I get 50 predictions, right? So I get y hat, let's say, for tree 1, y hat for tree 2, and so forth. And maybe tree 1 predicts class label 1, tree 2 predicts class label 2, tree 3 predicts class label 1, class label, let's say, 0 for tree 4, and so forth. And then we do a majority vote, look at which is the most frequently predicted label. And in this case, we can maybe say class 1 is the most frequently predicted label. So for example 1, example I, we can say predict class 1. And we would repeat that for all the data points, right? For I up to n. So we get a predicted label by majority vote for each training example. And based on that, we can then compare it, or we can just look at what the correct label is in the data set, right? Because we have the actual labels, and compute the accuracy from that. And this would be then our out-of-bag accuracy estimate. Yeah, and we could actually do something similar to compute the feature importance. So let me clear the screen and then do some more annotation here. So how does the feature importance via permutation then work? So one thing about this is a very specific version here for the random forest where I talk about trees. But later in a later video, I will also talk about a generalized version for that using a separate holdout set that doesn't have to be, it does not have to be the OOB dataset. So in this case, if this is a little bit short and a little bit complicated, don't worry so much about this, because first of all, this method B is not used in scikit-learn anyways. And later we will see a more, I would say, generalized version, which is, I would say, more popular in practice because we can use it for any type of method. And I will also have more visualizations later to make this more clear. So here, this is more like the short version of how that can be specifically used in the context of random forests. So first step would be counting the votes for the correct class. So we could also, let's say, compute here the accuracy. I think the same thing would also apply. And let's say we count the votes for the correct class for a given decision tree or across all the decision trees. And what we then do is we consider a feature J and permute this feature in the OOB examples of a tree. So consider we have the out-of-bag examples here, and we have here the training examples for the rows. So let's say training example 1, or maybe training example 3, and training example 5. And then the columns here are the features. So let's say this is feature x1, feature x2, and feature x3. So what we do is we pick a feature. Let's say feature J is here feature 2. We pick it and we just randomly shuffle all the values here in this column, right? And then after we shuffled these values, we count the number of correct votes again afterwards, after permutation. And then we look at how much it has changed. So how much has the number of correct votes changed. So we could also actually do the same thing with the accuracy. How much would the accuracy would have changed after shuffling, right? So it gives us an indicator of how important that feature is. The more the number of correct votes changes, the more important the feature is, right? Because the decision trees in that case have heavily relied on that feature to make a prediction here for these data points, right? So in this case, the permutation, the shuffling, kind of tells us how heavily is a feature used in the decision trees, and in that case, it's kind of correlated to how good the predictions are before and after shuffling. And then we do that, of course, for all the trees in a random forest and average the importance over the trees, and we repeat this for all the features, and then can also normalize these values such that they sum up to 1. And this would be a different way of computing the feature importance. But like I said, we will be revisiting a generalized version of that, the shuffling principle, when we talk about wrapper methods in a future video. So also with that, I want to end this video. We talked about filter methods before. Now we also finished the discussion on embedded methods. It was actually a long story, but all I wanted to say is that there are some methods where feature selection happens internally, like in L1 logistic regression, where some features become 0, and in decision trees, where decision trees select different features. And there are also these random forest feature importances in random forests, which are somewhat related to the feature selection in decision trees. And in the next video, we will talk about these wrapper methods, which are more explicit about selecting features. First of all, more explicit in terms of using a criterion or something like even the accuracy here as a concrete thing we want to look at to derive the feature importance. And they are also explicitly using models. We can control which model we use and so forth. And as we will see then in the next videos, it's actually very powerful. It's computationally more expensive than, of course, like filter methods, for example, but they can be also very powerful, as we will see.